Okay, so we'll get cracking. So the three sections will be the first three questions on the test after Easter, and now we're going to look at tonight the last two questions on that test. I'll be going as fast as possible without rushing, if I do go fast over something, do stop me, and there's the video as well. I'll have that up probably fast enough tomorrow. Okay, so let's see what we're looking at. So the things that we've been studying, actually not in this module but in your previous module, were functions of a single variable, and these are in engineering you can think about them as relationships between variables. So for example, there's a relationship between the area of a square and its side length, and you can say that the area is a function of the side length. In fact, the area of a square, the S there, not standing for square, standing for the side length, is the side length squared. It isn't that the S causes A or anything. The important thing is that for each value of S, there is a single value of the area. So that's what a function is. So for example, when S equals 3, the area is equal to 9. Something like this. So for the language is little s here is the independent variable, and this is the dependent variable. This depends on this. So the idea is that if you know what the independent variable is, you automatically know what the dependent is. We'll just fire a load of examples at you there. The height of a projectile depends on time. At each time, there's a certain. So if when I let go of this, it's time equal to 0. For each time after 0, there is an associated height. Yearly sales of a product. So for example, say a product is on sale for 3 years. There is one number that describes the yearly sales. The temperature of a component is a function of time. You're using something for 20 minutes. After 20 minutes, there is a temperature at that time. You can do stuff with beams, no? Yeah. Little bits of beams. So you've got loads of things: load per unit length, shear force, bending moment. I take it you didn't do slope. You did?
Yeah.
You did. Okay. So slope is actually what slope looks like, and the deflection is how below the horizontal, and all of these depend on the distance along the beam. So if you've got a beam with length 6, you go distance 5 across, you have at that point the load per unit length, the shear force, the bending moment, the slope, and the deflection. The speed of an object is a function of time, acceleration is a function of time, loads of stuff. Loads and loads and loads of stuff. You don't have to get into it. The volume of a sphere, something like this. Okay. Now what we're going to get into in this section is, of course, a lot of things in engineering have a slightly more complicated relationship. For example, very, very simple example, the area of a rectangle depends on 2 numbers, not just 1. Or the volume of a rectangular box depends on 3 numbers. Or you have things that depend on loads and loads of numbers. So this is what's called a function of several variables. So I will just look at a little bit. So consider the bending moment on a light beam of span 6 meters subject to a constant UDL load. Looks something like this. The bending moment is a function of a single variable, the distance along the thing. And what we plot then is, say for example, on the x you plot the distance, and on the y you have the bending moment at that point. So for example, if it's simply supported load at the end of the beam at 6, the bending moment is 0. So you plot input, output. Many functions in engineering, physics and mathematics tie together more than one variable. For example, this is the bending moment on a square plate. I assume you haven't done something like that, but you can imagine a similar story. You've got a plate and it deflects as well, and I don't know, does it actually look like that? I'm going to guess that it does. The plate is somehow simply supported all around the edges, so if you can imagine the plate, and it's just kind of simply it's just kind of off a ledge at the edges. Do you know what I mean? Mm-hmm. Imagine just loads of supports around the sides, and it's a constant load. The bending moment will look like this, and it depends on 2 numbers, the 2 coordinates. like, so you need two numbers to describe a position on the plate, and this is what the bending moment looks like. Okay. How the bending moment varies as we change x and y is easy to see from the graph, but if you want to adapt the tools of one variable calculus to help us investigate functions, blah blah, we want to do that. So in other words, we want to look at really kind of slopes, rates of change. We'll talk about how slopes are a little bit difficult, but certainly rates of change. What happens to the bending moment as we walk in the x direction, for example? Something like this. For the most part, we will look at functions of two variables, but everything kind of extends. Usually in the maths, you'll only see functions of two, but it works the same. If you 3, 4, it works the same. Okay. So some examples: the area of a rectangle depends on the width and the length. For beams, the slope and the deflection, they depend on the distance, but also the material of the beam and the cross section of the beam. So the deflection and the slope depend on 3 variables. And arguably, if you're talking about a load that's different, maybe the deflection also depends on the load. No, it does, but in a particular way. Did we say Eve any electronics? No, okay. Don't mind the third one. The fourth one, the volume of a cylinder depends on the radius and the height. Okay. So these things, if you want to plot them, so with the single variable things, like the bending moment, you plot number in, number out. 2 numbers, 2-dimensional graph. These things, there's 2 numbers in and 1 number out. So you have to plot something with 3 coordinates, so the graph of a function of 2 variables is 3-dimensional. So it looks something like this. So for example here, consider this function, x and y in, x squared plus y squared out. So if you put in x equal to 1, y equal to 2, you get out 1 squared plus 2 squared, 1 plus 4 is 5. And so we should see the point 1, 2, 5 on this. So maybe something like, I don't know, x equal to 1, y equal to 2, z equal to 5. 1, 2, 5. You put in the number 1, 1 into this, you'll get out 1 squared plus 1 squared, so 1, 1, 2 is also on this. And consider all the possible inputs, calculate all the possible outputs, graph all those 3-dimensional points, you get a surface. Now there's loads of different ways that you want to be interested in this. The best reason really is you'll be talking about, do you do anything with fluids, thermal fluids? A little bit, right. So you'll be doing things, you probably hear in the next few classes, you'll hear stuff like what happens to the temperature when the pressure increases. But you'll hear something like the temperature kept constant. Let me try again. What happens to the temperature? What happens to the pressure when the temperature changes but the volume is kept fixed? Or what happens to the
increase or decrease?
Pardon?
It changes?
It changes. But what happens if you keep, say, the volume constant? And you change the temperature, what happens to the volume?
Pressure.
Yeah, pressure, yeah. These kind of questions you'll hear, so you'll see one thing changing, so you got something, let me just write something down here. So say, I think the one I really want to think of is pressure depending on volume and temperature. Now, I could equally write down temperature depending on pressure and volume. Maybe the first one makes a bit more sense, maybe, I don't know. So the pressure depends on the volume, the pressure depends on the temperature, and there'll be questions like, how does the pressure change when the volume changes but the temperature is constant? Or how does the pressure change when the temperature changes, the volume is constant? This kind of thing is what this is useful for. It's also, in theory, can be used for maximizing things. So there's a question here, what is it? Maximize it's saying maximize the volume with some constraints, or there's another one here about, I think it's something like minimizing heat loss. So you can do these kind of questions as well. Right. Now, so I want you just to imagine that this mountain here it's in 3D, and I want you to imagine that it's the graph of a function. So the height is z is a function of x and y. So it's a graph of a graph of, say, this z thing. Just like the graph, the surface we had with two of them. This yoke, 3 dimensions. This yoke, 3 dimensions. Imagine this is one of those graphs. And imagine you're at this point here, and imagine that's somehow down the bottom of the mountain. Now, we'll put a bit of analogy into this, in that we'll say x into the page. So that's north. Yeah? Yeah. So x, more or less, well, x plus anyway, is north. And as you look at it, y is west. Okay. And the question is, how does the height change as I walk north? Going up. It goes up, yeah, it does. Now, it depends on the room, so the thing underneath we might change. Do you know what I mean? The east-west can turn around. So, what is the rate of change in z as I keep y constant? When you're heading due east, it's not east for us, it'll be north. There's no change in your east-west. So imagine there's the mountain there in front of you, y is west, x is north, z is the height. If you walk directly north, do you move east-west? No. And similarly, and this is the thing, right? If you're a person standing at a point on a mountain, particularly when the peak is right in front of you, and if it's just a hill, you can talk about the slope, because usually when you're on the mountain, you're only going in one direction. You're going up to the top. Of course, if you meet a sheep, and you ask the sheep, what's the slope? Depends. What does it depend on?
Where do you go?
Where are you going? What direction? So it doesn't actually make sense to talk about the slope at this point. It does straight up the mountain, but what about walking that direction? The sheep might be going that direction, or that direction, it depends. And the two directions that we're going to be interested in, now I have northwest there, that we'll kind of get rid of them in a second, but it's going to be x and y. The slope in the x direction and the slope in the y direction. We aren't going to look at the slope in other directions, but it's not a million miles. If you really wanted to know, you go and Google it, right? We're just going to look at the slope in the x and the slope in the y. Yeah, I think that's okay. Right, so what we're going to do is, if you're walking directly north, essentially you're just walking up the curve. So this is the side view of you walking up the mountain. Okay, taken as a side view of the surface. Now this is the thing we need. It's, if we're going in the x direction, y is a constant. So this is for some fixed constant y. We're not saying specifically what it is. Maybe we'll just show it down here. So this is, so say y. I'll just say y0, constant. And you can see this here. So I think we'll be moving, x will be probably, I'm not sure. If I walk due east, I don't move north-south. And if I walk south, I don't move east-west. And if you walk straight up the mountain, going directly north, or in this picture directly x, this is what you have. Okay, so it makes sense to talk about the slope of the tangent. So it makes sense to talk about the the slope in a given direction. Okay. Now you can talk about rate of change, you can talk about slope. Now if you just look at this for a second, so this is at a fixed y, so this is just a, if you just kind of think of it as, so I've got b here, maybe just scratch out this y0 just to be consistent, call it b. So you're at a fixed y value b, so ultimately this z is a function of x and b, and if b is a constant, then really the height just depends on x. So this is actually just a function of x. In other words, you look at your coordinate in the north direction, and if you're going straight up, you automatically know how high up you are. So the question is, you want to get the slope. How do you get the slope of a function of x?
Due to the derivative.
Derivative. So the rate of change, or the slope of this thing, well, we'll just write this down. This is df dx, which is the same as f dash of x. So it's just completely normal if you fix the constant y. Right, so what we're going to be doing is we're going to be looking at the derivative, or the slope in the x direction and the slope in the y direction. But when we do it, when we're going in the x, y is constant, and when we're going in the y, x is constant. Okay, so we'll have a look at one of these. So what is the rate of change of z with respect to x when y is fixed at 2? Now I could substitute in the y equal to 2, but we're not going to be doing that. Most of the time we're not going to specify what y is, we're just going to say y is fixed. So I'm going to keep I'm just going to write y equal to 2, but I'm not actually going to evaluate it. So I'm going to rewrite this z. I'm going to write it as x cubed plus, now for reasons that will become clear, I'm going to write the y cubed before the x squared, and I'm not going to write y cubed is equal to 8, I'm just going to keep 2 cubed times x squared minus twice y cubed. Shit, 2 cubed. Okay, so this is one particular route up, say that's the height of the mountain, this is one particular route up the mountain going in the north direction where the east-west coordinate is 2. And the question is, what is the rate of change, what is the derivative? We need to differentiate this with respect to x. So we're going to write this as dz dx. What is the derivative of x cubed?
3x squared.
3x squared. How am I going to differentiate 2 cubed by x squared? Fix the 2 cubed, yeah. Fix the constant. And then what's the derivative of x squared? 2x. And then finally, what is the derivative of minus 2 by 2 cubed?
0.
0. Because the thing in red is a constant. The derivative of a constant is 0. And I'm not going to tidy it up, I'm just going to leave it like that. So basically what we're going to do is we're going to do that, except we're not going to be specifying that y is equal to 2. We're going to keep, this is just going to be y cubed, and this is going to be 0. Okay, so what we have is something like this. The rate of change of z respect, so we're going to have, so this will be so differentiating z with respect to x and y is fixed. I'm just going to write something down here. It'll be something like, if z is equal to f of xy, the rate of change of z with respect to x, you're just going to differentiate f and have the y fixed at b. But actually what we're usually going to do, I'll just write something else now in a second. Usually we kind of need to get to the examples. It's kind of confusing, it's difficult to explain this. So what we're going to define is partial f partial x. Now, if you ask me what this symbol is, it's just a math symbol. It doesn't really appear anywhere else but this context. It's like this, and it's called partial. What it's about is you're looking at f changing with x, but everything else is constant. Now, we're just talking about going north where east-west doesn't change, but if you have something that depends on multiple variables, you can still do this. So say there's 50 variables, this would be looking at the rate of change of f with respect to x, and all the other 49 variables are constant. So this is the same as more or less the derivative of f with respect to x, given that y is constant. So it's the same as looking at the slope in the x direction purely. And the other one, the partial derivative with respect to y, is differentiate with respect to y as normal, but keep the x constant. Right. Let's see an example here. Okay, now I'm going to do the one with respect to y first, for